So good afternoon, everybody, and my sincere thanks to the organizers for giving me this opportunity to be here in this wonderful meeting. So I am Raka Dasgupta from University of Calcutta, and I am going to talk about Josephson oscillations in atomic molecular Bose-Einstein condensates and also the effects of stochasticity on it. So here goes the brief storyline. So we are starting with the generic mechanism of Josephson oscillations in ultra-cold bosonic systems. Then we'll consider a specific case of atomic Bose condensate to molecular Bose condensate crossover and study the particle dynamics as well as the phase dynamics. And then we shall discuss how the incorporation of noise in the system is the game changer. And then I'll wrap it up with a summary. So about bosonic Josephson junctions. So just like two superconductors when connected via a thin insulating layer can give rise to Josephson oscillations, any two weakly coupled macroscopic quantum states can show similar behaviors because now the potential barrier between the states play the crucial role of that intermediate insulating layer. And one classic example is that of a double well, BEC Bose condensate in a double well. So now the particles can tunnel from one well to another and come back again. So this is the Josephson oscillation. And because Bose condensates are intrinsically nonlinear in terms of the interaction they are in, the dynamics is far richer because now the oscillation is like a swing. It can go from one well to another and can come back. But the dynamics itself can play the role of a crucial influencer that determines when to push the swing and when to stop it. And so beyond a critical coupling, it can happen that the swing is pushed to one particular corner, meaning in terms of particle dynamics, most of the particles are localized in one particular well. So it is the effect of the nonlinearity that can lead to particle localization. So this is the example of a double well. So the theory was developed way back in 1997 that so up to a certain coupling, the oscillation is kind of symmetric, meaning both the wells are equivalent to the particles. But beyond that, there is a clear mandate, meaning one particular well tries to draw more followers. The overall average number of particles is concentrated in one of the wells. And this is the experimental signature. So you can see that initially the red blob, meaning the particles are evenly distributed. Sometimes it is in the left well, sometimes it is in the right, but beyond a certain coupling, it enters this self-trapped regime where it is always the one of the wells which is more populated than the other. So there are several variants of the system that had been studied. And the particular case we want to focus is that of atomic BEC and a molecular BEC, a mixture of both, where two atomic bosons can join hands to form a molecule through means of Fishback resonance. So in this case, instead of two wells, as in the double well case, the atomic state and the molecular state, they play the role of these two wells. But since the form of the interaction is different, so the consequences are different as well. And here, this is the crucial Fishback resonance parameter, which can be controlled via an external magnetic field, and that is an adjustable parameter of the system. So the dynamics can be described in terms of the relative population and the relative phase among the two states. And the equations follow that of a pendulum-like motion, only now the length of the pendulum is a variable, the string. String is a variable one, so as the bob goes away from the midpoint, the length changes. So if we study the dynamics of the system, there are two curious cases that stand out. One is that, suppose I start with an initial relative imbalance 0.6. So below a certain parameter value of the Fishback detuning, what happens is the entire oscillation profile is above this 0.6 value. And then after a certain point, the entire profile comes down of this 0.6 value. So this is not exactly a phase transition kind of thing because no non-analyticity is involved, but this certainly is a crossover because above 0.6 meaning now the atomic state is favored more, where below 0.6 means the molecular state is favored more, and the change occurs at a certain value of the Fishback detuning. And if we study the phase dynamics, another curious incidence occurs is that the dynamics changes from pure oscillatory behavior to some linear plus oscillatory that people term as running mode in literature. And this indeed is a sharp transition, because if we study that, we observe that if we use the expected value of the population imbalance as some kind of an order parameter, it shows a cusp exactly at the point where this oscillatory mode to running mode transition takes place. And if you look at the phase trajectories, the phi z in the phi z plane, the oscillatory mode can be mapped to these closed orbits, meaning if you complete a one-time period, you come back to the same old phi, where the running mode means if you complete one period, you go to phi plus 2 pi. So this is the change that we are talking about. And now suppose we include some noise in the system. So the two sources can be one in the Fishback coupling, and another place could be the Fishback detuning. Suppose we incorporate wide Gaussian noise in both of them with strengths gamma A and gamma B respectively. So now one convenient way of studying the system is, instead of this Z phi, you just write them as block, something like block vectors Lx, Ly, Lz, though they do not follow the standard commutation rules, but the system can be solved in terms of that. And since this Lz is again a measure of the imbalance, so just by mapping this system to the traditional block equations, we could identify the relaxation times, and it seems that the particle dynamics is governed by the relaxation time is governed by gamma A, meaning the noise strength of the Fishback coupling, not the Fishback detuning. And what happens to the particle localization? So if we remember that in absence of noise, it was like this, that at a certain parameter value, the entire envelope, we started with 0.5 this time. So the entire oscillation envelope was above this, and then it came below this. So earlier it was an atom heavy state, and now it is a molecule heavy state. But now the mere incorporation of noise, be it the noise in the coupling or be noise in the detuning, what happens is you may start with the molecule heavy state, but as time goes on, gradually the system is shifted towards the atom heavy state. Meaning that in the same parameter regime, you can have both the atom heavy state and the molecule heavy state, depending on which time you are looking the system at. Okay, thank you. So I'm almost done. So this is the summary in short. So we were discussing the crossover from atomic Bose condensate to molecular condensate via Fishback transition. We saw that there is a particle localization crossover, meaning the system goes from more atom side to more molecular side as the detuning is varied. And also there is a transition in terms of the relative phase between the two types of condensates. And the inclusion of, after the inclusion of the noise, we saw that the relaxation dynamics of the population imbalance is governed by the noise in the Fishback coupling only, and not in the Fishback detuning. And now the mode atom and mode molecule states can sort of coexist. I mean, meaning for a fixed set of parameters, you can either have the mode atom state or the mode molecule state, depending on which time scale you are looking at. So that is all from my side. And for the acknowledgement part, the initial part of the work was carried out by Swati, who was a master student with us in University of Calcutta. So the initial part was her master's thesis. The part with the noise was developed in collaboration with Abhinavo, the PhD scholar. His poster is also there outside, not of this about this problem, but another one. And we are grateful to Professor Shubina Dasgupta for a discussion regarding the nature of the phase transition. So that is all. Thank you. And a small announcement that from 18 to 23rd December 2023, we are having the STATPHYS Kolkata 12 meet organized collectively by all the institutes and universities in Kolkata. So all of you are very much welcome there. Save the date. Thank you.
Okay, time for questions. Yeah, Okay, let's thank the speaker. Thank you, ma'am.